Hi everyone, my name is Adrian Balajadia and I'm a grade 10 student from St. Mary's High School. And today I would like to present to you my 2022 CYSF project, BlindNavo, an outdoor navigation apparatus aiming to assist the visually impaired utilizing computer vision and computer science obviously, GPS, Google Directions, and the Raspberry Pi 4. So let's get into it. Vision is a very important human sense. Whether it be making breakfast in the morning or helping us complete certain errands or chores, it is present in almost every aspect of our life. One way that we use our vision is to self-navigate through the outdoors whenever we take a simple walk in the park or a simple trip to the grocery store. For people that already have adequate vision and could already see well, this might not seem much of a problem. But for the 2.2 billion people in the world and the 1.5 million people here in Canada that are visually impaired, this simple trip to a convenience store could already become quite a problem or quite a challenge. Although there are methods that blind to low vision people use to get around, such as landmark identification, which is the process of identifying certain unique objects in a familiar environment, although these blind to low vision people use these techniques, in terms of unfamiliar or entirely new places, blind to low vision people still face certain difficulties trying to self-navigate to their desired destination. So to address this problem, for the 2022 CYSF, I decided to make use of my knowledge in computer science to provide a potential solution to this. The main objective of this project was to create a wearable, lightweight apparatus that could aid the blind and the visually impaired people self-navigate to any destination in the constraint of Google Maps. So since the aim of my project was to create a lightweight apparatus that could help the visually impaired people self-navigate to any destination that they wanted, I of course needed hardware that was light and compact and ideally that could fit in a cardboard box. It's for that reason that I used the Raspberry Pi 4 as the main motherboard that would direct and execute most of the software in my project. Along with the Raspberry Pi 4, I also included the Pi Camera 3, some headphones, a GPS module that would keep track of the user's location, as well as a small USB microphone that would record and receive input from the blind user regarding which destination that they want to go to, for example, and I also implemented a small push button that would allow the blind user to reset the entire system if they no longer wanted to use it. And compiling all of that hardware brought about this prototype in the end of my development phase. Here you can see the different parts of the hardware that's in the apparatus. So we have the GPS model that's over here, the USB microphone that's this little black thing over here, the push button here, the wired Apple headphones. The Pi Camera 3 was installed at the front, and this is what it looks like through an inside perspective. So here we also have a miniature breadboard that connected the push button and the GPS model through jumper wires to the Raspberry Pi 4, and of course everything needed to have a power source, and I utilized a portable 5-volt charger that would power everything. So moving on from the hardware component, I would also like to briefly describe the key software components in my apparatus system here. And one of the key software components involves object detection, and for the purpose of obstacle avoidance and warning users of these obstacles ahead of time, which is one of the problems and difficulties that blind people faced, according to some literature I review. And obstacle avoidance and obstacle detection refers to drawing the bounding box and warning the users of the certain items in the sort of items detected in that bounding box, in these bounding boxes. And one of the object detection models that I used was efficient det, and efficient det, according to the authors, is scaled accordingly to a resource constraint, which is the floating point operations per second, and it is very compatible with the Raspberry Pi 4 because the Raspberry Pi 4 isn't, of course, as computationally powerful as a computer. So the series of efficient models seem to be perfect for the Raspberry Pi 4. In addition to obstacle avoidance, another challenge I wanted to address was warning the user of nature of dynamic pathways such as roundabouts or curved sidewalks, like in this photo. And an applicable computer vision domain was semantic or image segmentation of sidewalks. And in this section of the software, I used the DeepLab V architecture, and I created certain confidence intervals which determined the walkability of certain areas or regions in the image. And I took inspiration from a certain research paper. So as an example, since this interval had the highest confidence score, then the route recommendation would have been a slight right to stay on the crosswalk here. In addition to that, I also use the Google Directions application programming interface, which means API. So I use the Google Directions API with the Bayesian 220 GPS to keep track of the user's location and to provide relevant directions. And in addition to that, I also use the Google Text-to-Speech to, of course, transcribe the voice input from the blind user, and of course to provide audio messages and voice commands to the user. And due to the time constraint of this video, I can't properly go in depth with the type of software that I use, but I would just like to point out that there is a more detailed explanation and there's more information in regards to this available in my full report in the online CYSF platform. Now that I've talked a little bit about the hardware and the software that was involved in the creation of this apparatus and the navigational device, I would also like to present a little bit of a demo and just to showcase how an actual user would use this product. So to activate the device, the user or the individual has to press the button. And after pressing the button, the device will ask the user where they would like to go.
7-11 New Brighton Drive.
Then the device asks them to confirm their destination.
Yes.
Then it says to take the first direction, which could just be going straight for 50 steps. In this clip that the apparatus uses the Google Directions API and the GPS model to track the user's location and to give them voice directions. And it's in this clip that you would see the apparatus invoke the object detection model to tell the user that there is a person in front of them. And in this example case, since the user is veering off to the right, away from the sidewalk segmentation model would be invoked here and would tell the user to take a slight left to stay on the sidewalk. So throughout my testing phase, I took around 12 walks during the months of January and February, and it's in these walks that I tested out different aspects of my model, such as the object detection, if the GPS and the Google Directions API was working, or if the sidewalk segmentation model was accurate. And one of the biggest modifications I made was with the program architecture, actually, and it turns out that to speed up the inference time, I needed to add some concept called multiprocessing to my code. And another major modification that I made was with the object detection logic, because in my observations, initially my object detection logic was actually previously flawed, so I had to make modifications to that. Despite these modifications and changes I made to my project, unfortunately, I couldn't proceed to the next phase of testing, which would have involved me actually walking around blindfolded. Similar to the software component of this presentation, unfortunately, I can't go just as in-depth with my observations and results, but of course, there's my online project available on the online CYSF platform that has a great amount of detailed information regarding that. But regardless, thank you for listening to my project, and thank you CYSF for allowing me to present yet another science fair project.